All right, welcome back again, everybody. Today we're going to be continuing with Chapter 8, covering Section 8.2, and this is where we get to learn all about polar curves and polar equations. This is a pretty fun section, I think, because it gives you a new way of figuring out how things work and how things look, and there's a lot of pretty pictures. So there's also some cool interactive examples. So if you follow the links in the slides, you can follow along with the lecture if you'd like, or you can look at it all later too if you want. But there's some really, really cool interactive examples that we're going to see in just a minute. So let me pull up the slides. Here we go. All right, polar equations and polar curves. We're also going to get to answer that question of why even learn this stuff? Like who cares about polar coordinates, all that kind of stuff. We're going to see why in this section here. All right, so this is a little bit of a longer section in terms of stuff to cover. I will say that this is not a bunch of stuff that you really have to memorize, but you should get comfortable with it, and we're going to see a whole bunch of examples. So we'll start with polar equations, just what they are. Then we'll talk about polar curves. We'll discuss symmetry in the polar coordinate system. Then we're going to see specific examples of how to graph lines, circles, cardioids, limaçons, roses, lemniscates, and spirals. So we get to graph all of these cool things using polar coordinates. All right, so let's talk about polar equations first. So an equation whose variables are polar coordinates is called a polar equation. So in essence, it's still an equation, but now the variables are representing polar coordinates instead of Cartesian coordinates. So we're not thinking in terms of x and y. We're not thinking in terms of horizontal displacement, vertical displacement. We're thinking in terms of radius and angle swept out. So if we've got a function, r equals f of theta, this is a function that tells you what the radius is going to be at a certain angle. So this is the key idea. R is a function of theta. So each value of theta is determining a radius, or you could think of it as a distance away from the origin. Really, it's a displacement from the origin, but just for ease, we'll think of it as a distance for a moment. And that's really what it is. So you plug an angle into this function, and it tells you what the radius would be at that angle. So that'll tell you like how far out to go from the origin. Then you put in a different angle and it'll say how far out to go from the origin. Then you put in a different angle and it'll say how far out to go from the origin, and so on and so on. So that's a polar function or a polar equation, a function that will give you polar coordinates. So why is this stuff helpful? Why even learn any of this? Well, a lot of times when we're investigating stuff in reality or in our imaginations, stuff behaves rotationally or radially, right? Where it's kind of like you don't necessarily want to talk about stuff in terms of rectangles. You want to talk about stuff in terms of distances away from a single point, right? So distances from an origin. So it's like, hey, if I'm staked right here at the origin and I shoot out this direction a certain distance, where would I be? And then if I turn this way and I shoot out this distance, shoot out this way a certain distance, where would I be? And then you can keep doing that. So this stuff happens a lot. This stuff happens a lot. And that's why we want to learn about these things. We want to get comfortable with polar coordinates. We want to get comfortable with polar curves, and we want them to feel just as natural and intuitive as the curves that we've been looking at since we first learned about the XY plane. So the graph of a polar equation given by r equals f comma theta, or more generally, f of r theta equals 0, which you'll see later on. The graph of these things is the solution set to those equations, just like in the past, and that's what we call a polar curve. That's really it. So a Cartesian curve is the curve that the types of curves you're familiar with from before. These ones are still curves. Now they're polar. All right, so let's try this one. Let's express this as a polar equation first. Excuse me. And what this means is convert this equation so that it's in terms of r's and thetas, right? Right now it's in terms of x's and y's. Those are Cartesian coordinates. If we want to represent it in terms of polar coordinates, we have to use the isomorphism equations to convert. So here's how we're going to do it. We're simply just going to substitute. Although maybe I'll say this first. This is really just the parabola y equals 1/4 x squared. So if you look at this equation here, and you divide both sides by 4, you'll get this right here. So graphically, This quite literally is the parabola that I just drew right here, roughly, that I sketched. So in terms of Cartesian coordinates, that's what you've got, right? So that's the object that we're describing, but it's described as pictured and as written initially in terms of Cartesian coordinates, but we can equivalently describe it using polar coordinates. And the way that we do it is we substitute in the values using the isomorphism equations. So remember that x is r cosine theta and y is r sine theta. So when we plug those values in for x and y, we're changing the equation into the form of a polar equation. Now we can do some simplifications. We've got this. We could divide both sides by r squared, right? R squared. Or no, I'm sorry, just r. As long as r is not 0. If r is 0, we're going to be at the origin anyway. So when r is not 0, we can do this division. And then just simplify some things, right? So we'll get r equals 4 sine theta over cosine squared theta, which simplifies to this. There we go. Now, this is where you should just pause and ponder this a moment. So I'm actually going to I'll throw up the thinker for a minute. Just ponder what this is saying. Okay, so hopefully you had a minute to think about it. But what this is saying is that this parabola that I sketched up here is described equivalently in polar coordinates using this equation. So this equation down here, r equals 4 secant theta times tangent theta, that is the polar representation of this parabola. That's it. That's how you describe it in terms of polar coordinates. Here you go. Here's a picture of it. Let me zoom in a little bit. So you see it's still the same parabola, but now it's given in terms of polar coordinates. Pretty cool, huh? So every curve that you've seen, every Cartesian curve that you've seen in the past, it has a polar representation. It has a polar representation. Let's try this example here. Let's convert r equals 4 secant theta into its rectangular form. So first I want you to think about how you would do it. How would you do it to start? All right, now say something out loud to yourself about how you would do it. Okay, and then try to do it yourself. See if you can convert this equation so that there aren't any thetas or r's, but there are only x's and y's. All right, now let's do it together. So if I want to get back to x's and y's, I'm still going to have to use the isomorphism equations. I'm still going to have to use this right here. X equals r cosine theta, y equals r sine theta, and I've got secant theta here. Well, secant theta is 1 over cosine, so r equals, this is like 4 over cosine theta. And then if I multiply both sides by cosine theta, I get r cosine theta equals 4. Oh, but check this out. R cosine theta is x. So this is the equation x equals 4. And that's just the equation of a vertical line, right? The equation of the line x equals 4 looks like this in terms of Cartesian coordinates. So as bizarre as it might sound, this equation right here, this equation right here is describing this vertical line, the line x equals 4. But up here, it's described in terms of polar coordinates. Pretty wild, huh? And it's really fun when you think about it like this. Remember, this equation that we're given here, the polar equation, it's telling you what the radius is when you're given an angle theta. So quite literally, it's saying, hey, if you tell me an angle, then how far out you need to go from the origin is given by 4 times secant of that angle. So as the angle theta goes around and around, so quite literally, you could imagine theta going around the origin like this, right? The angle goes around and around. The radius is going to depend on this function right here. So basically it's going to go like this. Maybe I'll draw some of these. Maybe I'll use green. Here we go. So when it'll be like this, right here, right here, right here, right here, here, and it keeps going. So as the angle theta sweeps around, the radius is going to grow and grow until it's infinite, right? Pretty interesting. And here's a picture. Oh, sorry, this is just what I did. X equals 4. So this is a picture of it. Notice that it's literally just this vertical line at x equals 4. That's it. So we saw how to describe lines. We saw how to describe that parabola. Let's do another one. Let's convert r equals 2 sine of theta to its rectangular form. So again, I want you to try this one on your own. So let me put up the thinker and the speaker. So first, think about this for a minute and then say something out loud about how you would try to do it yourself. How would you convert this to a rectangular equation or a Cartesian equation? All right, now try to work it out on your own. See if you can get this into the form y equals something with x or x equals something with y. All right, now let's do it together. Let's see, we're given r equals 2 sine of theta, but that's about it. So I think I'm going to go to my slides before I mess anything up. That's right, that's right. So there's a nice little trick you can use here. Multiply both sides by r, and then you get r squared is equal to 2r sine theta. And there's some cool results here if you think about it like this. Let me get my little blue pen here, right? So we know what r squared is. R squared is x squared plus y squared. But we also know what r sine of theta is. R sine of theta is y. So boom, just in that one step, we can convert to having only Cartesian coordinates, x's and y's. So then we get this result, x squared plus y squared minus 2y. And this is the equation of a circle. It's the equation of a circle, but we don't know the center or anything yet. We don't know the center or the radius yet because it's not in standard form. It's in general form right now. So the way that you can convert it into standard form is you complete the square. So with completing the square, you're just going to add and subtract a special value that will let you turn part of the expression into a perfect square trinomial. And so we'll get this result here. And that's because of this piece right here. Let me highlight it. This right here factors into y minus 1 squared. Then you can move the negative 1 to the other side, and lo and behold, you get this. So that's the equation of this circle with radius 1 centered at the point 0, 1. And that's what this equation is describing. So r equals 2 sine theta is a circle with radius 1 centered at 0, 1. Here's the picture. There's the picture of it. So in terms of Cartesian coordinates, here is the center, 0, 1, and the radius is 1. And so this is the circle that we're looking at. Not too bad, right? Not too bad. Okay, let's do another example. So how about this one? See if you can now sketch the polar curve, now that we've seen some examples of polar curves. See if you can sketch what this one would be like. Let me do this right here. So yeah, think about it and then try to write something down. What object is described by the equation r equals 2? Okay, now let's talk about it together here. Notice theta is not mentioned anywhere in this equation whatsoever. So this does not depend on theta at all. All this tells us is that r equals 2. And so if the only requirement is that the radius is 2, then we're just going to get a circle centered at the origin with radius 2. So quite literally, It's this, where this is 2. That's what this equation is describing. R equals 2. Let me go to the next slide here. Yeah, there we go. A circle of radius 2 centered at the origin. Yeah, this is totally independent of theta. So any angle that you want to use is admissible. So all that matters is the radius here is 2. And this also brings me to another point to give more meaning to this. This is one of the reasons that polar coordinates can be really, really handy and really, really nice, because we can describe this entire circle here that you see in the picture using just this basic equation. R equals 2. That's a circle with radius 2 centered at the origin. In comparison, if you wanted to write it in terms of x and y coordinates, like Cartesian coordinates, it would be this, right? It would be x squared plus y squared equals 4. So which is simpler, r equals 2 or x squared plus y squared equals 4? Depends, right? So maybe in your context, in your application, in your work, it would be much easier just to use this. Maybe you really, really need it to be in terms of rectangular coordinates, so you want to stick with this. The point is you can pass between either or, and you get to choose. You get more flexibility. Okay, now how about this one? So see if you can do this one on your own. Think about it out loud first. What do you think the curve would look like? Okay, now say it out loud. Say something out loud about what you suspect the curve might look like. All right, now sketch it. See if you can sketch it, and then we'll compare our answers in just a moment. All right, here we go. So the first thing that I notice about this equation is that there's no mention of r anywhere. There's no mention of a radius, literally nothing about a radius. So that tells me that the radius is basically a free variable. This equation, this relationship that we're describing, does not depend on the radius of a circle. The radius could be anything. The only thing that this equation is stating is that the angle swept out must be pi over 3. So because of that, and because the radius doesn't matter, this is just going to be a line that passes or coincides with the ray given by the angle pi over 3. Let me sketch it. Right? So here's the angle pi over 3. And again, it doesn't matter what circle we're talking about. All of these circles are admissible. All that matters is that the angle there is pi over 3 from here to here. So it could be up here or down here, and that's the picture. So this is the equation for a line passing through the origin that sweeps out an angle of pi over 3 with the polar axis. Excuse me. There it goes. So that's what it looks like. Let me zoom in a little bit. That's how you can describe an angled line like that in terms of polar coordinates. And again, thinking about like the flexibility and freedom of these things, all of that is contained in this one equation here, that theta equals pi over 3. That's it. That whole line is contained in that single statement, which is pretty cool. All right, so on a different note, let's pause and talk about symmetry in the polar coordinate system. So we talked about symmetry in the Cartesian coordinate system. For example, symmetry about the y-axis, symmetry about the x-axis, and then symmetry through the origin, right? Like even and odd functions, for example. So you can still have symmetry in the polar coordinate system, but the symmetry equations are a bit different. So here, there's this one. If a polar equation is unchanged when you replace the angle by its opposite, then the curve is symmetric about the polar axis. Remember, the polar axis it coincides with the x-axis. So this is the polar axis. Here's the origin. And what this is saying is, hey, if you've got some function like r equals f of theta, and nothing changes if you replace it with f of negative theta, then what that means is it doesn't matter if you went clockwise or counterclockwise, you would get the same output. And so what that means is you're going to have symmetry vertically about the polar axis. And that's what's being pictured here. So if you notice this picture here, let me go to this color. The curve in question is this pink one. Looks kind of like a light bulb, right? And that curve, that pink light bulb, is symmetric about the polar axis, the x-axis. What that means in terms of a polar equation is that the function is even in some sense, right? It's even, but now it's reflection about the x-axis. Pretty cool. So that's one form of symmetry you can have. You can have another form of symmetry. So if your polar equation is unchanged when r is replaced by negative r, or when theta, I'll say this, or when theta is replaced by theta plus pi, then the curve is symmetric about the pole. And here, this picture is a good example too. This is actually what's called a lemniscate, and we're going to see an example in just a few minutes here. But this curve is symmetric about the pole. And so what that means is that if you change the sign of the radius, it does not change the result, right? I'm sorry, I shouldn't say that. Yeah, that's right, that's right. It remains unchanged when r is replaced by negative r. And that's what we get right here. So here's an example. Um, do, do, do. Yes, yeah, exactly. So you've got symmetry through the origin, just like this. All right, and then one more. So if your polar equation is unchanged when you replace theta by pi minus theta, then the curve is symmetric about the line theta equals pi over 2, which is the vertical line right down the middle, the y-axis. Oops, let me make that a little cleaner right here. So this is the line theta equals pi over 2. And so what this is saying is if you replace your angle with pi minus theta, then you're symmetric about this line. And those are all three of the symmetry properties for the polar coordinate system. All right, now let's talk about how to sketch these curves. So what we would like to be able to do is get some intuition and get some deep understanding about how to draw these things by hand, because you have that for Cartesian curves, and you've been sketching in terms of Cartesian coordinates for many, many years. So now, once you go through some math courses, you can kind of get an idea of what the curves look like just by looking at the equation. So for example, if I write something like this, y equals x squared, for most, if not all of you, there should be a picture of a parabola that pops up in your head. We want to try to develop at least the foundation for you to have that skill when you see something like this. Something like this. What does 1 plus sine theta look like in terms of polar coordinates? That's the idea. So the fun thing is this. If you want to get an intuition for how this curve looks, or honestly, if you want to be able to sketch this curve by hand, the easiest way is to first sketch the curve in terms of Cartesian coordinates. So let me pull up this slide right here. So remember that what's happening here is this function is describing the displacement from the origin. Oops, there we go. So this is telling you the radius. It's saying, hey, when the angle is this, go out this far from the origin in this direction. Hey, when the angle is that, go out that far from the origin in that direction. And so it's really, really handy to graph these functions in terms of Cartesian coordinates first, and then to read that graph to draw the polar curve itself. So what's sketched right here, this is a graph of r equals 1 plus sine theta, but it's given in Cartesian coordinates. So we're essentially going to pretend that theta is x and pretend that r is y, and we're going to sketch a curve just like we did earlier in the course, right? We had like a whole bunch of sections on graphing these curves, and they were on like the first test, I think, too. So this is the thing you need to be able to do, and this is what's going to come up again when you get into Calc 2. So this is the part you really, really want to remember. You want to be able to graph trigonometric functions comfortably. So when you see something like y equals 1 plus sine of x, you want to be able to graph that comfortably. And the way that we're going to interpret that Cartesian graph is this way. This is telling you how far away from the origin to travel as you go around the circle. So on the x-axis here, we're actually plotting angles. So as the angle goes from 0 to 2 pi, the radius is going to behave like this. That's how it's going to go. And we're going to see a really good interactive example in a moment. But just off the top of, or off the bat, we can see something like this. When the angle is 0, the radius is 1. So basically at angle 0, we're going to go out 1 unit from the origin. And then when the radius, I'm sorry, when the angle increases to pi over 2, now we're going to be going out 2 units from the origin. And then as we continue along and go to pi, we're going to be going out a little bit less, a little bit less, a little bit less. And then at 3 pi over 2, the radius is actually 0. So in this case, we're not even going to have any displacement from the origin. So at 3 pi over 2, when you're facing down, right, when you're facing like downward, this direction, pointing down, you're not going to go anywhere. You're going to be stuck on the origin. And that's how we interpret it. So this is this is basically a picturization, a pictorialization of how it would trace out as you went around. So when the angle was 0, we went out 1 unit. When the angle was a little larger, we went out that far, and then this far, and then this far, and then this far, and then this far, and then we can literally graph the polar curve just by going around the circle, or I should say around the origin, and going out that distance. That's the whole idea. So here's the whole construction all on one slide. So basically these 3 arrows are corresponding to these 3 arrows over here in the construction of the drawing. And then you would keep going. So let me zoom in down here. Right, so here's like the first part. Then as you continue around, as theta increases and goes from pi over 2 to pi, these green arrows are going to go out like so. Notice you see the arrow, the red arrow indicating the direction of theta, the parameter. There we go. And then we're going to keep going. So now down here, after we go from pi to 3 pi over 2, the arrows get a little bit shorter, right? That's exactly what's happening up here. You can still see it right here. See, as we go from pi to 3 pi over 2, the radius is decreasing down to nothing. So what that corresponds to on our picture is these arrows are going to start this long and they're going to shrink down to be very short until they're nothing. Then once we get past 3 pi over 2, let me erase this. Once we get past 3 pi over 2 and go to 2 pi, the distances increase again, the radiuses increase. So starts at 0 and they get longer and longer until they go back to 1. And voila, that's the final picture. And that's what we call a cardioid. So the equation that we're looking at, this r equals 1 plus sine theta, this actually describes what we call a cardioid. And we're going to see a bunch of examples in a few minutes here. All right, so that's the idea. Now let's do an example and I want you to try this one. So see if you can sketch the polar curve r equals 2 sine of theta. So think about how you would start it first. Now say something out loud about how you would do it. How would you start this? Oh, looks like my slides are cutting out on me. Come on, no. Hold on. All right, welcome back again. Sorry for the technical difficulties. Let's see. Oh, that's right. So you were going to be graphing this polar curve, and the idea was you want to start by graphing it in terms of Cartesian coordinates, and then to use that graph to make the polar graph. And the way it works is this distance here, this displacement, gives you what the radius is at all of these different angles. So at all these different angles, it'll tell you how far out to go from the origin on your polar graph. And for this curve, notice that you'll go out and the radius will increase until you get to pi over 2. Then it's going to decrease as you go from pi over 2 to pi until it's down to 0. So these x-intercepts on your Cartesian graph correspond to touching the pole in your polar curve. So if I kind of match the arrows that I drew on the Cartesian graph, they should look something like this, 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 and this. And then as I circle around, or I should say, as I continue to go around from pi over 2 to pi, my radii decrease in length until they're 0 again. Now, this is what's interesting about this curve. When you go below the theta axis, the radius is negative. And remember, when you have a negative radius, you reflect through the origin, right? So these red lines, what's actually going to happen is you're pointing in these directions, but the radius is negative. So you're gonna shoot back through the origin. You'll actually be going this way. And so what happens is you end up getting this circle again. And so lo and behold, this curve here, that's the circle with radius 1 centered at the point 1 comma 0. There we go. Or I'm sorry, 0 comma 1, 0 comma 1. Okay, now how about this one? So this is another one. You should try this one on your own. See if you can figure out how you would start. And then try to work it out on your own, and let's see what you get. We'll do it together in just a moment. All right, here we go. So this is the graph of cosine 2 theta in terms of Cartesian coordinates. So this is the type of graph that I'm hoping you're much more comfortable graphing now that we did those sections earlier in the course, because that's really what's going to help you. Once you graph that, just read off what the radii are going to be as you go around the circle, and remember that they're going to be negative if this curve dips below that theta axis. So right here, from 0 to, what is that going to be, pi over 4, your radii are positive. Then there's 0 at pi over 4, then they go negative, like so. So let me see if I can write the corresponding arrows over here. So at the very beginning, this is the first arrow, that green one. Then it goes like this. Then they start shrinking down to 0, and right when you get to pi over 4, you're at the pole again, right? Then what happens? So then what happens is the radius goes negative. So as you go from pi over 4 to pi over 2, the radii are negative. So rather than shooting out this way, they're going to be reversed. So we're actually going to be shooting out this way, like so. And then you can keep going around and around. And maybe what I'll do here, just to show you what this looks like, if I were to try to trace it out from start to finish without drawing those arrows, the trajectory of the curve looks like this. Actually, let me annotate it first. The trajectory of the curve looks like this. This way, this way, this way, this way, this way. Then it goes this way. Then it comes up this way. Oops. And so on. So here's how it's really being graphed. Oops, here we go. So it's going to start here at this point, and then it's going to go this way, and then around, and then around, and then around, and then right back. Let's see that again. Like so. That's what the curve looks like. That's the trajectory of the curve. All right, so now what I want to do is I want to pull up this interactive GeoGebra example. Let me get it pulled up here. Okay, let me pull it up right here. I think I hid it just so it wouldn't take up so much memory. Okay, let's do that. Where is it? Where are you, Chrome? Hold on one second. Oh, there it is. Ah, okay. All right, so let me go ahead and do this, and let's take a look together here. Let me move OBS for a minute. All right. Okay, so again, you can follow the link that said an interactive GeoGebra example. This is just a free website where you can do all sorts of cool stuff, so please explore it and have fun with it. But this is going to show you how this all works in like in an animation. Sometimes it's easier to make sense of in an animation. So the curve that we're looking at here is cosine of 3x. So this is the standard cosine curve, but twice as fast as normal. And just like I was showing you before, there's this green arrow here, and that indicates the displacement from the pole. This is the Cartesian curve of cosine 3x. And then what's going to happen is it's going to produce the polar curve over here. So let me just start by doing it manually, and then I'll let it run. So if I let theta increase from 0, it's going to trace the curve out for me. You see it? There we go. Okay, let me let it run, see what it looks like. There we go. See, it traces out that curve. When the radius is negative, the ray is reversed of what it normally would be. But that's how you do it. That's how you do it. Okay, let me stop. We can put in another one too. Let's do which one were we, how about we do 2 sine of x? That was the one we saw in the previous example, right? Let's see what it looks like. Up and up and up. Maximum radius goes back down to 0. And then once it gets to 0, it reverses. See, now even though the angle is in between pi and 2 pi, the radius is negative, so it's still shooting back around. All right, and then you can do all sorts of cool graphs with this thing, and it'll literally show you how to trace them all out. So again, I encourage you to play with this, put in some funky functions, whatever you want to do. Oh, what about if we did something like secant x? Let's see what happens there. Oh, oh, that looks familiar, right? That's right. Just a vertical line, right? There you go. So now you can see how it's traced out. And again, you can make up whatever function you want. What was the one like secant x, tangent x? That was one we had earlier, or something similar. Let's try that. Secant x, tangent x, that was that parabola. That's right. There it is. And then again, even though the radius is negative here, or I mean, because the radius is negative, that means that the displacement is going to be flipped from the direction that it normally would be. Okay, so again, I encourage you to play around with this, experiment, plug in your own functions. These are in terms of polar coordinates, right? They're being graphed in a Cartesian system here and a polar system here, but I highly encourage you just to play and mess around with that and see what you get. Then we're going to be looking at this Desmos demonstration next. So let me go back to the slides. There we go. And let's take a look at the next thing. All right, so now there's a whole bunch of different types of common curves. So there are, if I look back at the very beginning, let me pull this up real quick. There we go. So we're now going to look at lines, circles, cardioids, limasones, roses, lemniscates, and spirals. What I was saying earlier is that you don't need to memorize these formulas, but you want to be able to comfortably graph these types of things. So we're going to see how they look on Desmos. Here we go. Okay, so these are the equations for a line. So actually, let me do this so I can see this a little better. Oh wait, no. There we go, there we go. Okay, so these are the equations of a line. So if a is a real number, then this equation, r sine of theta equals a, that's the graph of a horizontal line in the polar plane. And a will tell you how many units above or below the pole you are, depending on the sine of a. And then if you used cosine instead, r cosine theta, that one's going to be a vertical line. That's why secant was giving us a vertical line, right? R equals secant theta. In that case, a was 1. This will give you a vertical line that lies to the left or right of the pole, depending on the sine of a. And yeah, so now what you can do is if you click on that Desmos link, it'll bring up what we're about to look at right now, which is this. Okay, so I have all of these different kinds sketched out here in Desmos, and we're just going to look at a couple of them right now. So here's what lines looks like. Right now, a is equal to 1, and here are the two formulas for it. So as I increase a, if you'll notice what happens is when a gets larger, it moves away from the pole. As a goes down to 0, it coincides with the pole at 0, and then it goes below. So these are the horizontal lines given by the equation r sine theta equals a. Now let's look at the vertical lines. So these are vertical lines, and they're given by the equation r cosine theta equals a. And so as a changes, it moves left and right. So that's what lines look like. Okay, next let's look at circles. So before I do that, let me transition back to the slides here. So circles have these equations. So again, we're starting with a real number a, and this equation here, r equals 2a sine theta, that is a circle of radius a centered at the point 0, comma a in rectangular coordinates. And then this one, r equals 2a cosine theta, is a circle of radius a centered at the point a, comma 0 in rectangular coordinates. So that's the formula for circles. Let's check it out. So now we'll hide the lines. Let's see the circles. So this is a circle of radius 0.2. Here are the equations for it. And as I increase a, I should say this. This is just the r equals a is just a circle centered at a, right? I'm circle centered at 0 of radius a. This is what we saw earlier. That's r equals a. Now let's look at r equals 2a sine theta. So here what's happened is you've got this circle, and as I change a, it changes the radius. So the lower pole there is touching the pole. I should say the lower coordinate down here. This is touching the pole. And as I change a, it increases the radius. If I want to look at the cosine one, it's on its side. There you go. Oh, if a is negative, then it goes to the other side. Pretty cool, huh? So those are circles right there. Okay, now what's the next one? Let's go back to the slides. Cardioids. So cardioids are actually given by these equations here and here. So it's essentially the radius is given by a plus a cosine theta, or a plus, or a minus, geez, a plus a cosine theta, or a minus a cosine theta, and then the same thing for sine. So let's look at the example. All right, cardioids, here we go. In this case, a is negative, I'll make it positive. So this is what a cardioid looks like. Uh, Cardioids get their names because they look like hearts. So if you think like, cardiac, that kind of thing, that's why they're called cardioids, because they've got this heart shape. And if I increase a, it kind of increases the radius, you could say. And then as I shrink a, it shrinks down to the pole. One thing about cardioids is they do always contact the pole itself. So there's a point where the radius is 0, just like that. If a goes negative, then it switches sides, right? Oh, sorry, let me show the formulas. So that was 1 plus cosine theta. If I do 1 minus cosine theta, it's just the other side. There you go. Roughly like that. So again, this is something you can open up and play with on your own, and I encourage you to do so. What about the sine ones? Those ones will be on the top and the bottom. There we go. Like so. All right, now let's see the next example. All right, so those are cardioids. Now let's talk about limasones. So limasones have a similar form to cardioids, except now we're allowing this coefficient to be different than A. And just so you know, limaçon is the French word for snail because these roughly resemble snails. And what you're going to see about limaçons is that as long as A and B have the right size relationship, there will be a little loop. There will be a little inside loop. So let's take a look. All right, limaçons. Here we go. So this is a limaçon. Here's the formula. So this one is A plus B sine theta. Right now I have A at 1.2 and I have B at 2. So 1.2 plus 2 sine theta looks like this purple curve right here. And if I change A, it changes the size of it. And notice here that if, where is it? Right there. So if A and B are equal, then I get a cardioid, which is exactly what we saw a moment ago, right? Because then you would have A plus A sine theta. So that's a cardioid. And then if A is bigger than B, what happens is the little point that would normally contact the pole starts to move away. And if A is less than B, we get an inner loop right there. And they can invert. They can invert. There you go. So these have the form A plus or minus B sine theta. What happens if I change B? It changes the size of the loop. There you go. Or cosine. So if you wanted to do the cosine examples instead, they're just on their side instead, which kind of makes sense. Generally speaking, that'll be the relationship. If it's sine, it's going to be like above or below, and if it's cosine, it's going to be to the left or the right. All right, so those are limasones. What's the next one? Let's see. So we did cardioids, limasones, roses. So these ones are called rose curves. So let a be a real number and let n be an integer. So n is just going to be any integer like, 1, 2, 3, 4, 5. Then rose curves are given by these equations, a cosine n theta and a sine n theta. And the curves resemble a flower. That's why they're called rose curves. In my opinion, they look more like daisies, but that's just my opinion. And also we have this cool result. If n is even and not equal to 0, then the rose will have 2n petals. And if n is odd but not equal to -1 or +1, then the rose will have n petals. So you can always tell this stuff immediately if you get really familiar with these equations. Let's take a look. Okay, so roses. Aw, there we go. See, lots of pretty pictures, lots of pretty pictures. So here I've got n equals 2, and these are the formulas. So a sine n theta, a cosine n theta. And as I increase a, that just increases the diameter essentially, right? But then when I increase n, that increases the number of leaves or the number of petals. So if it's odd, there are n petals. If it's even, there are 2n petals. There we go. More and more and more and more. Pretty cool. So those are the roses. Sine and cosine look very, very similar. They're just rotated a little bit, which makes sense. So here's the ones that for cosine. You decrease the number of petals here. There we go. And that's why they're called rose curves, even though I think they look more like daisies. All right, what's the next example here? So the next one are lemniscates. So lemniscates are given by these equations, r squared equals a squared sine of 2 theta, and r squared equals, oh, sorry, that should say cosine, typo. This should say cosine, cosine 2 theta. The word lemniscate comes from the Latin word for ribbon. So these they kind of resemble bow ties, and they also look like the infinity symbol. So the infinity symbol actually is a lemniscate. Let's take a look. All right, those are roses. Let's see lemniscates. There we go. That's what it looks like. And if I change A, you can see that it gets larger or smaller. And because Desmos actually can't interpret r squared equals a squared sine 2 theta as a function of theta, which it's not because it's r squared, right? I had to do each one individually. So I did a root sine 2 theta, but you'll get the same result either way. So that's a lemniscate. And again, you can play around and explore these more if you would like. Now let's look at the last examples. So the last examples are spirals. So there's two types of spirals that I have graphed here. One of them is called an Archimedean spiral, and it's given by this equation. The radius is a plus b theta, where you alter a and b. Changing a changes the start of the spiral, and changing b changes how many spirals there are. And then there's also logarithmic spirals. So these are functions that you might be familiar with in Cartesian terms. These are just exponential functions, and that's why they're called logarithmic. That's why the spiral is called logarithmic, because logarithms and exponentials are inverses of each other. But this is essentially changing, again, kind of like the size and the frequency of the spiral. So let's take a look. All right, we're going to go back to this. Spirals. Okay, let me zoom out a bit. Which one do I have drawn first? Okay, so I have the Archimedean spiral first. R equals a plus b theta. And if I change a, you can see that it kind of like it moves the location of it. Let me lower b a little bit. Here we go. There we go. So it changes the starting point of the spiral when you change a. There we go. Right, and then if I change b, that's going to change how tight the spiral is. So if b is very large, the spiral is not very tight, unless I zoom out. There we go. Oh, it's also ending here because I have a bound on theta. So theta can only be as big as 12 pi. That's what I had written there a second ago. But now if I change B, you see it kind of like tightens the spiral up or stretches it out. And then if I move A, it kind of like moves the center a little bit. There we go. There we go. That's the idea. So that's an Archimedean spiral. Sometimes it's called an arithmetic spiral because as you can see, like the distances between these spirals is equal. So it's like an arithmetic sequence, basically. You're just adding a common difference to get to the next part of the spiral. Now let's look at a logarithmic spiral. Let me lower these a little bit, shrink that down a bit, shrink B a little bit. There we go. So this is what a logarithmic spiral looks like. And you can see this is different from the Archimedean one because it's not uniform. Like the distance between the parts of the spiral, maybe the periods of the spiral, are not uniform. They actually expand in size as theta increases. And that's because, again, this is an exponential function, right? So it's going to grow exponentially if b is positive, and it's going to decay exponentially if b is negative. So let me zoom in again. Let me go back to the home here. Let's make b negative and watch what happens. Whoop. Now we get a tight little spiral that's spiraling inward. If b is positive, it spirals outward. There you go. I'm overwhelming Desmos here. Okay, let's zoom back in. All right, let's go negative on b again. Oh, and b is 0, you just get a circle. Why is that? Well, if b is 0, then you have e to the 0, which is 1, and then you have a times 1, which is a, so you'll have the equation r equals a. There you go, and that's a circle. All right, so if b is negative, you get a tight little circle there. I'm sorry, a tight little spiral there. Let's zoom in on it, and it's logarithmic. There you go. Like I said, lots and lots of fun pictures. I encourage you to play around with these and explore on your own. And I think that's it. Let's check. That's it. Let's play. So once again, I am sorry about the technical difficulties. Hopefully they weren't too distracting. But yeah, so again, you should play around with these. Go to GeoGebra, go to Desmos, try to graph some of your own, and just see how these curves work and get comfortable with them. All right, I'll stop there, and I'll see you all next time.